Now I want to tell you a little bit about atomic interactions, because everything I told you, I mentioned collisions and everything, but I did not define a little more precise atomic interaction. And so I would like to do, and I'm going to just jump through a few things so you can understand the concept of scattering length. I know again that many of you already know, but you know, it's never too much to review. So the most part of the gases we're working with, they are diluted. Okay, so the density is not that high. If the density is not that high, the most important effect of interaction is what we call two-body interaction. If you have too many particles, there is a good chance that three particles get together, and this is a process that's called three-body interaction. Okay, and three-body interaction is not like pairs of two. No, it's a complete different interaction. Okay, but here, in most part of what we're going to do, even though in some condensates, people are already seeing three-body types of effects and many-body types of effects. But normally, to understand most of what we're going to do is a diluted gas, and then the dominant process is two-body, two particles colliding. And then we have to understand this two-body type of effect. And two-body type of collisions, it's everywhere in the process of cooling. Like when you produce a MOT, a magneto-optical trap, you have a lot of collisions going on there, two-body collisions. When you have in the magnet trap, we already saw elastic and elastic collisions that are essential for evaporation. When you are in the condensate, even though there is no light, atoms are in the background, there is also interaction. In fact, most of the properties that we observe with quantum gas relies on interaction. So it's better to say a few words about interaction. And when we speak about interacting particles, we have to speak about potentials. And if you take two particles in the ground state, most likely the potential type you have is what they call van der Waals, at least at long range. And van der Waals, as you know, is this oscillating dipole type of force that appears and is present almost everywhere in nature, and is one of the main interaction responsible for the chemistry that we live. Okay, so imagine you have those two atoms coming together. The potential between those particles normally has this shape. Of course, most part of the atoms we're going to do, they share electrons. So you have to speak about the triplet and singlet type of state, right? And the triplet here is when the spins are parallel, or you are in a total one spin if it is a two-electron system, and the singlet is zero. And because of the symmetry introduced by the spin, as you know, the spatial form of the potential, which is basically the spatial form of the wave function, is different for singlet and for triplet. So if we imagine here, you know, and we go, the shape always has this very big barrier. It's a strong repulsive core, that's how we call. It has an attractive tail at long range. So when atoms are apart, they normally attract each other. When they get very close, they repel. And this potential is being well investigated, and everybody, and normally we have a leading term, which is one of our six, but there are other terms as well. And we normally, the traditional van der Waals interaction is given by this term, and this C6 as being measured and calculated for many of the systems we're going to work with. And as you know, hydrogen has a small C6, and the alkalis have a big C6 because of the polarizability, right? So normally, you see, they interact a lot. And this here is giving in units of atomic units, that for C6 is the electron charge times the Bohr radius to the 5th power. And normally the other coefficients, as you can see, they are not so important. Remember, they are bigger, but they go with the larger power, so they just disappear almost. So this is normally the interaction between the atoms. And when they are very cold, when the momentum of those atoms are not so big, we have to come with the concept of scattering length. Because scattering length is a quantity that somehow resume all the interactions present in this system. So I'm going to fast show to you what is the scattering length that everybody going to speak about, and try to show why we can manipulate, as Vanderlei was saying yesterday, that using magnetic field you can go up and down and make positive, negative, and so on. So to tell you about the scattering length, we have to show some scattering. And the scattering problem in physics, you have an income wave. Here we're going to do all quantum mechanically, right? So you have an income flux and you have an outgoing flux. And normally we picture this in the following way. Imagine you have two atoms, and here I put v over 2 of velocity for each because I want a relative velocity which is v, just for my calculation here. So in fact, this is a wave coming. It's close to a plane wave coming. And encounter this in the relative motion coordinate. You have this plane wave coming, and then they collide, but the product of a collision can go everywhere. So normally we picture in the following way. There is a plane wave coming, and there is a spherical wave going. This is the typical scattering problem that we learn in the first course of quantum mechanics. But when the atoms are approaching, there is interaction. So imagine you have this plane wave coming, right? So the plane wave is coming at long range. One atom does not feel the other very much, so you have this type of oscillation. It's like a plane wave, a sine wave, or whatever. And then when they get together, they either accelerate if there is attraction, or they decelerate if there is repulsion. So if we see the outcoming wave, it is either a little bit advanced or a little bit delayed, right? Compared to the no existence of potential situation. This is what characterizes what we call phase shift. And most of you already learned that, and I even calculate phase shift from potentials, right? And so this phase shift, somehow if I look from far, the phase shift has to give me information about, as an overall, how was the interaction. Because if the wave is a little delayed, or if it's a little advanced, I can know if the potential is effectively attractive or repulsive. So the thing we're going to do is relate the phase shift with the interaction. And in the low energy limit, this relation gives me the scattering length. So the concept of scattering length is a concept that tells us about interaction, okay? Okay, but we have to write a wave for this process. So the wave that represents the system is a plane wave, which is the incoming channel, and is a scattered wave, which is the outgoing channel. Right? And as I showed to you in the picture, the income is a plane wave, and the outgoing is a spherical wave. So, normally, the income wave, this is like sines and cosines, which is the plane wave. Now, the spherical wave, which is given by this, everybody had a chance to see a spherical wave already, either in optics or in quantum mechanics. So this is the spherical wave. But because of the characteristic of the potential, you don't expect the amplitude of the spherical wave to be the same everywhere in space. So you have an amplitude which is theta dependent, depending on the angle. This we call the amplitude of the scattering, right? So this is an easy way of writing things. And turns out that for very low energy, this F function, which is the scattering amplitude, is a constant. And I'm going to show you why it's a constant, at least very briefly. And this constant we call scattering length. It's A. But because it's independent of angle, right? So that's why we call S wave. It's no angle dependent. And if K is very small, because we are talking about small energy, right? The only thing that can be small is the momentum. If the momentum is very small, basically the exponential is 1. Right? So this function here at the low energy limit gets this form. So in the low energy limit, the wave function of this scattering problem is this. It's a function that extrapolates to 0 exactly in the internuclear separation that is equal to the scattering length. In fact, that's the way we measure. We go measure the wave and we extrapolate to 0. We see that in doing photo association, or there are techniques to measure this. Okay? So this is the scattering length. So the scattering length is in fact the scattering amplitude in the very low energy limit. Now, how is this scattering length connected to the phase shift? To do that, I'm just going to recall you that that amplitude of scattering is basically the differential cross-section. Right? I'm not going to give you detail in here because otherwise I'm not going to advance. So F to this amplitude square, and this can be a complex function or anything, right? As everything in quantum mechanics. Right? It can be complex, but when you go to measure, it's real. So this is the differential cross-section. And if this is a constant, bingo, this is a constant. So I integrate in the angle, and I get the cross-section, which is only dependent on this constant. Right? So I integrate, if this is a square, the integration gives me sigma, and this gives me 4 pi. So the cross-section is completely related to the scattering length. And if we go a little further in this scattering theory, we can normally, when you solve the equations, right, for the scattering problem, we find we can express the amplitude of scattering in terms of polynomials and in terms of the phase shift and the angular momentum involved in this process, which is L, right? This is the angular quantum number. But if it is very low energy, K is so small, and remember, if I have a very low momentum, I can't build up angular momentum. If I have a very small linear momentum, I cannot build up. So it's S wave, there is no angular momentum. L is equal to 0 for very low energy scattering, because basically Rk is the angular momentum. And I cannot build even a h-bar unit if K is very small. So as you know, I stay to 0. So this is what we call S-wave scattering, because there is no energy enough to build up angular momentum, right? So this is S, only L equal to 0 contribute, because it's very low K. Then the cross-section here is I just put L equal to 0, and I give this. And if I have a small phase shift, just expand this. And you find out, if you compare this with 4 pi a square, you can automatically get that the phase shift is basically the momentum times the scattering length. And as you saw, it doesn't matter the shape of the potential. Everything turns to be one number that characterizes the interaction. So we use that all the time because we are in this regime. So all the interaction is characterized by the scattering length. And the scattering length, if you have that potential that I just showed you, is a number, finite number. For one state, it's one number. But turns out that the atomic system is not as simple as a simple potential. You have many potentials there. And you may be facing a situation where you have potentials like this, right? Like the singlet and the triplet is an example of this. But you have more than that. You have a hyperfine. You have all kinds of energies there that provide you different potentials. So all kinds of interactions. So you may have, suppose you have a particle, forget about this potential here. Normally we have a particle coming here, it bounces and goes back. And then there is a phase shift, and then there is the scattering length. Right? This is what we call an open collisional channel. Comes and goes. But we may have what we call a closed collisional channel. Closed collisional channel means that particles cannot be in that guy in the asymptotic regime, right? I start there, I come, I may interact with everything, and then I leave. So if you have a situation like this, imagine that this is total energy, and my particles are colliding. They have translational motion, so the total energy is a little bit here. When this energy matches the energy of this closed collisional channel, right? Because particle cannot get in there. There's no energy. But it feels, because the quantum mechanics is made of a lot of interference. And then the existence of a possibility of a bound state here affects very much the way the particle interacts in this region. So normally when my translational energy matches this, I say I have a resonance. And people has investigated this in nuclear physics long time ago. The principle of Feshbach resonance is not from atomic physics, from nuclear physics, right? And so in this case, the scattering length and the phase shift and everything else is very much affected. It can go, it can have different signs because of the interference of this free channel, where the collisions are coming, with this closed channel, which is a bound state present in there. And because of those potentials, and this is called Feshbach resonance. So somehow the scattering can go very big because of this matching. And what's interesting here is that because I can use external field to put this level up and down, because of the Zeeman shift, or even the Stark shift, what I can do is do the following. I can come with a magnetic field and raise up or put down this whole potential here. And the levels goes together. So I have a way of tuning this using external fields. And this process, well, let me tell you, that's a second order process. Particles start in that open collisional channel, interacts with the closed channel, and leaves in the open channel. So you have two particles colliding that potential, and then they are intermediate. They feel that during the interaction, but they leave, they decay and leave in that potential that was the beginning. Okay? And this whole interaction makes the scattering length to modify the shape. In fact, when my translational energy is equal to that energy of that state, I have a singularity there. And this is what Kettle wrote yesterday. And of course, there are people that do this calculation very precise, considering all those channels and all the coupling and everything, and comes with theoretical relations. But they normally look like this. And I manipulate this guy. I don't manipulate this. What I make is this bigger or smaller than that, and that changes the sign. That's why you saw that dispersive type of curve. And you're going to see many of those during this school. Everybody got that? So this is the concept of scattering length, and that's how we manipulate scattering length. Okay? Okay. So normally, you can show that the scattering length can be written as a scattering length plus a term here that can be very big if I use a magnetic field as a tuning parameter for these levels. I've been very explain things so otherwise, but any book you take on scattering theory or in atomic collisions, there will be details on this, okay? And even I can follow, so I'm sure all of you can follow. Then people has measured scattering length. I'm going to jump to this, but this is to give you an order of magnitude. for the values. This is in atomic units. Remember, atomic units for us in length is the Bohr radius, right? Which is about 0.5 angstroms or 0.05 nanometers. And you see there are systems with a huge scattering length and can be positive or negative. And that has very big consequences on the characteristic of the condensation. The magnitude, the size of the scattering length, as well as the sign. Okay? And then you have people measuring, and there are very nice techniques on collisions to measure this, and I recommend you if you want to learn about this. There is a review of modern physics that we wrote 6 years ago, I think. And it's a very thick paper. It's not the one I hand to you. And it's only about atomic collisions in the ultra-cold regime. So you can learn there what are the techniques employed to determine those things. Okay, so this is a kind of introduction to the atomic interaction, and everybody be speaking about scattering length, so it's better for you to know. Now I want to change topics and start to speak about Bose condensation, right? Because so far I only spoke about other things. And I had a vision of going very far and show to you the real necessity of a chemical potential. But this is very well explained in a book by Feynman, Statistical Mechanics, and I'm going to jump to that because I was going to explain how comes that we need the chemical potential and what is the physical interpretation of it. But unfortunately, I'm going to have to jump, but I'm going to copy and give it to you, and it's almost self-explanatory, this, and turns out that you can understand and you can deduce from statistical mechanics. And you know, statistical mechanics rely on partition function. Partition function is how energy can be divided, right? And so everything has to come from there, from that principle, from that key principle. And what I did is start with that principle, introduce to you in the context of quantum particles in a system, why you need the introduction of the chemical potential, which is this little number here, mu. Okay? But I'm going to jump to this, give you the copy, and I will be here the whole time, so you can come and ask me. But if we do that, we can come with an occupation number that Ketel already showed yesterday, which is, if you have particles, a number of particles in a quantum system, and if there are bosons, and Ketel said very clear that nature loves bosons. So if you are a boson, you are in good relationship with nature. So you can share space with your friends, you can share energy, momentum, and everything.